Welcome to week 2 into the skeletal system. Last week we studied the integumentary system and reviewed the organization of the body. Now we turn to the body's framework. This is lecture 1 of the skeletal module, and you know the rhythm by now. Today, anatomy, physiology, and lifespan changes. Then lecture 5 covers the diseases, diagnostics, and medications, and lecture 6 covers your role as the MA. Here's the idea I want to correct right here at the start. Most people picture the skeleton as a dry, dead scaffold, the thing that's left over in a museum case. But that picture is wrong. Bone is living, richly supplied with blood, and constantly rebuilding itself. Roughly every decade, you replace your entire skeleton, one microscopic patch at a time. Bone is also a mineral bank, storing and releasing the calcium your heart and nerves depend on, and it houses the marrow that makes your blood cells. By the end of this lecture, you'll be able to name the divisions of the skeleton, describe the structure of a bone, explain how bone is continuously remodeled, classify joints, and describe how the skeleton changes from infancy through old age. It's a lot, and you might have questions as you go through. Take a look at the reference materials that we've provided for you, including your required textbook and the OpenStax free textbook that you can find under your Start Here tab in your Brightspace course. Here are our 5 learning outcomes for this lecture. First, list what the skeletal system does for us, and it's more than you'd guess, plus the 2 great divisions of the skeleton, axial and appendicular. Second, describe the structure of a long bone and understand the difference between the dense, compact bone on the outside and the lighter, spongy bone within. Third, identify the bone cells and explain remodeling, the lifelong process of tearing down and rebuilding bone. Fourth, classify joints by structure and by how much they move, and describe the anatomy of a synovial joint, the freely moving kind. And fifth, describe how the skeleton changes across the lifespan, from the growth plates of childhood to the bone loss of older adulthood. Keep these 5 in mind as the summary will loop back to them. Here are the medical terms that you need to know and understand this lesson fully. Take a moment to look them over. We'll use each of them as they come up in the slides ahead, so don't worry about memorizing the definitions just yet. Just get familiar with the words. As always, pause the video to take some time to take your notes. Let's start with what the skeleton actually does. There are 5 functions, and notice that only the first one is the one everybody thinks of, and that's support. Bone gives the body its framework and shape. Without it, you'd just be a puddle of mush. Then there's protection. The skull guards the brain, the rib cage guards the heart and lungs, and the vertebrae guard the spinal cord. Now let's talk about movement. Bones are levers. Muscles pull on them across joints, and that's how every motion you make happens, which is exactly why the muscular system is paired with this one this week. Then there's mineral storage. This is the one students usually forget. Bone is the calcium's bank. About 99% of your calcium is stored here in your bones, and when blood calcium drops, your bones can then release some. Because your heart and nerves need calcium far more urgently than your femur does. And blood cell formation. Red bone marrow inside the spongy bone produces your red cells, white cells, and platelets. That's a process called hematopoiesis. See it again in week 3 when we talk about blood. The green panel here gives you 2 numbers worth remembering. The adult skeleton has 206 bones, while a newborn has around 270. The thing is, we don't lose bones as we age. Many of them simply fuse together as we grow. The 206 bones sort into two divisions. The figure on the right shows them together in the body. The axial skeleton is the central axis. It's the skull, the vertebral column, and the rib cage. About 80 bones in all. These are the bones that mostly protect. They form hard cases around the brain, the spinal cord, the heart, and the lungs. The appendicular skeleton is everything that hangs off that axis, your appendages. That's the arms and legs, about 126 bones, together with the girdles that anchor them to the axial skeleton. The pectoral girdle, the shoulder blades and collarbones, attaches the arms. The pelvic girdle attaches the legs. And here's a clean way to keep them straight, which is the last bullet. Axial bones mostly protect, appendicular bones mostly move. The skull is a helmet, and the femur is a lever. This division matters clinically. When we talk about DEXA scans in the next lecture, we scan the hip and spine, one appendicular site, one axial, because those are where osteoporotic fractures do the most damage. Now let's take a single bone apart, using the femur-style long bone on the right. The long shaft is the diaphysis. The widened ends are the epiphyses, one at each end. Look at the two kinds of bone tissue. The outer wall is compact bone, dense, solid, and strong, built to resist the forces of weight and impact. Inside the ends is spongy bone, sometimes called trabecular bone, which looks like a honeycomb. It's much lighter, and that's not really a weakness. That lattice is arranged along the lines of stress, giving strength without a lot of weight. Nestled in those spaces is red marrow, where blood cells are made. Remember that term, hematopoiesis. Running down the middle of the shaft is the medullary cavity, which in adults holds yellow marrow, mostly fat, a stored energy reserve. Two coverings to know. The periosteum is the tough membrane wrapping the outside of the bone. It carries the blood vessels and nerves, and it's loaded with pain fibers, which is why a bruised shin hurts so much. And at the joint surfaces, articular cartilage caps the bone, providing a slick, cushioned surface where two bones meet. The last bullet is the one to take with you. Bone is richly supplied with blood and nerves. It bleeds, it hurts, and it heals, all because it's alive. Here's the physiology that makes bones living tissue. 3 cells, and the tug-of-war between them that explains most of the skeletal disease you'll ever see. Osteoblasts build. They secrete the bone matrix called osteoid and then mineralize it. A simple memory trick, B for blast, B for build. Osteoclasts break down bone. The process is called resorption. They dissolve the matrix and crucially release the stored calcium into the bloodstream. C for clast, C for carve away. This is how the body withdraws from the calcium bank when blood levels drop. Osteocytes are mature osteoblasts that get walled into the matrix they made. Far from retired, they act as the bone's sensors. They detect mechanical stress and signal where remodeling is needed. That's why bone thickens where you load it and thins where you don't. Why an astronaut in zero gravity loses bone and a weightlifter gains it. Remodeling is the continuous cycle of the two. Osteoclasts excavate an old patch, osteoblasts fill it with the new bone. Over roughly a decade, you replace the entire skeleton this way. And the green bar is the clinical punchline for the next lecture. When resorption outpaces formation, when the clasts outwork the blasts, you lose bone mass, and that's osteoporosis. Weight-bearing exercise, adequate calcium intake, and vitamin D all tip the balance back toward building. Now for joints. Bones would be completely useless without our joints. A joint or articulation is simply where two bones meet, and the useful way to classify them is by how much movement they permit. Immovable joints, structurally called fibrous joints, are held together by dense connective tissue. The classic example is the sutures of the skull, those jagged seams that lock the cranial bones into a protective vault. Slightly movable joints, the cartilaginous joints, are joined by cartilage. The intervertebral discs between your vertebrae are the example. Each allows a small amount of give, and stacked up the spine, a little movement at each level adds up to a lot. Freely movable joints are the synovial joints, and they're the ones you'll deal with clinically, like the knee, hip, shoulder, and elbow. They're also the ones that wear out, which is where arthritis comes in the next lecture. The card on the right opens one up. The bone ends are capped with articular cartilage, slick and cushioning. A joint capsule encloses the space. Inside is synovial fluid, which lubricates the joint and nourishes the cartilage. Cartilage has no blood supply of its own, so it feeds from this fluid. Ligaments connect bone to bone and give the joint stability. And tendons attach muscle to bone, transmitting the pull that produces movement. Two words worth separating now because students mix them up forever. Ligaments join bone to bone, and tendons join muscle to bone. Now to the lifespan, starting at the beginning. The fetal skeleton doesn't start as bone at all. It starts as cartilage, a flexible template that is gradually replaced by bone in a process called ossification. That's why a newborn skull has soft spots or fontanelles, and why a baby is so pliable. A newborn has about 270 bones. We don't lose any as we grow. Many simply fuse together during growth, arriving at the adult 206. Now the structure you need to know, because it drives pediatric orthopedics. The epiphyseal plate or growth plate. It's a disc of cartilage near each end of a long bone, and it's where lengthening happens. Cartilage cells divide, push the ends apart, and are steadily replaced by bone. As long as the plate is open, the bone can grow longer. After puberty, rising sex hormones cause the plates to close, converting entirely to bone, and lengthwise growth stops for good. This is why a growth plate fracture in a child is taken so seriously. Damage there can stunt or angle the growth of that limb. Finally, peak bone mass. Bone continues to become denser into the 20s and early 30s, and that peak is your bone savings account. The more you bank as a young adult through nutrition, calcium, vitamin D, and weight-bearing exercise, the more you can afford to lose later. This is what sets up the next slide. At the other end of life, the balance we discussed tips the wrong way. Once past peak bone mass, resorption gradually outpaces formation. The osteoclasts remove a little more than the osteoblasts replace, year after year, and bone density slowly falls. This happens to everyone, men and women alike. But women lose bone faster after menopause because estrogen restrains osteoclast activity, and when estrogen declines, that brake comes off. This is the central reason osteoporosis is so much more common in postmenopausal women, and why you'll see a biophosphonates and DEXA scans on their charts next lecture. As density falls, the spongy lattice inside the bone thins out. Bones become more porous and brittle, and a fall that a young adult would shrug off can actually fracture a hip in an older adult. Older bones also heal much more slowly. The joints can change too. Articular cartilage thins, joints stiffen, and the intervertebral discs compress and lose water, which is why people genuinely get shorter with age and why morning stiffness becomes familiar. Don't I know that? For your practice, this translates into three things: fall prevention, which is the single most protective intervention, adequate calcium and vitamin D, and weight-bearing activity. Because remember, osteocytes respond to load by telling the bone to strengthen. Motion, quite literally, maintains the skeleton. So let's summarize. The skeleton has five functions: support, protection, movement, mineral storage, and blood cell formation. 206 adult bones in two divisions: the axial skeleton of the skull, spine, and ribs, which mostly protects, and the appendicular skeleton of limbs and girdles, which mostly moves. A long bone has dense, compact bone on the outside and light, spongy bone with marrow inside, all wrapped in periosteum, capped at the joints with articular cartilage. Osteoblasts build, osteoclasts break down, and osteocytes sense mechanical stress. Remodeling never stops, and when resorption outpaces formation, bone is lost. Joints are immovable like skull sutures, slightly movable like intervertebral discs, or freely movable synovial joints like the knee with cartilage, synovial fluid, ligaments, and tendons. And 6, across the lifespan, growth plates lengthen bones until puberty closes them, and after peak bone mass in the 20s to early 30s, density gradually declines, faster in women after menopause. In the next lecture, we'll pull this to work: fractures and arthritis, X-ray and DEXA scanning, and the medications that protect bone. Here are the references for this lecture. Check them out if you need more info.